Okay, so I wanted to quickly review some of the topics that we talked about last time. Um, and basically, we are focusing on using vector functions to describe the motion of various vectors based on time. Okay. Um, and the vectors, the output is a vector, the input is a scalar, and the output could be a two-dimensional vector or a three-dimensional vector. Okay. And now we're going to focus on calculus for vector functions. And just as a reminder, whenever we're talking about calculus, we are talking about limits, derivatives, and integrals. So those are the um, kind of three different phases. And of course, derivatives are limits and integrals are limits. So we always start off with limits. Okay. I wanted to mention uh, there's notation that your textbook uses for the unit tangent vector. So the setup is that you have a vector function, right? So suppose you have a vector function, and we know that the derivative is also going to be a vector function, right? Input is a scalar and output is a vector. But now, if you want to consider the unit tangent function, then we have to normalize this derivative vector function. And the way to do that is to scale it. So you are scaling by a factor of 1 over the norm of that derivative, right? So this is a scalar, remember? And so you're scaling by this factor, and the result is a unit tangent vector. Okay, we talked about how do you compute the derivative of a vector function. You just differentiate each component, right? So if you've got r of t, and this is part of why you just write an arrow, because it takes a long time to try to create a look of bolding it. So it takes a long time to do this. So the faster way is to just write an arrow. So r prime of t is going to just be the derivative of the first component, the derivative of the second component, and the derivative of the third component. And this is assuming that r of t is like this, f of t, g of t, and h of t. So to get the derivative, we're just differentiating component by component. Now, for this curve here, we've got r of t is equal to the square root of t I plus 2 minus tj. We're supposed to find r prime of t and sketch the position vector, r of 1, and the tangent vector, r prime of 1. Okay, so the first thing I want to point out, is that r of t is of this format here. Square root of t is our first component function, and 2 minus t is the second component function. So if you write that as x is square root of t and y is 2 minus t, then you can, and it might have been a while since you did this, so just as a reminder, you can eliminate a variable by saying that x squared is equal to t. Does that make sense? So now we've got y is equal to 2 minus x squared. This is a graph of negative x squared plus 2. This would be a graph of a parabola facing downward and translated up. Okay, so now if we want to find r prime of t, we're just going to take the derivative of each component. So we need the derivative of square root of t. So if we've got square root of t, we need the derivative of that, and then the derivative of 2 minus t. Okay, now write this square root of t as t to the 1/2. Do you remember that? Okay, and now t, 2 minus t prime is just going to be negative 1. And now what is the derivative of t to the 1/2? We're going to use our power rule. That'll be 1/2 t to the minus 1/2. Okay? Now, the position vector r of 1, if this is the formula that gives us a vector, when we put in a value of t, we want r of 1, and that's just going to be the square root of 1, comma 2 minus 1. So we'll just have 1, comma 1. Okay? And now the tangent vector r prime of 1, well, if this is our formula for r prime of t, then r prime of 1 would just be equal to, we're just going to plug in t equals 1. 1 to the negative 1/2, comma negative 1. Now, what is 1 to the negative 1/2? That is 1 over the square root of 1, right? Times 1/2, negative 1. Okay? Because remember, the 1/2 means the square root, right? And then the negative means you're going to take the reciprocal. So we just end up with 1/2, comma negative 1. Okay. Now, what I did was I used Mathematica. So the thing I want to do is I use Mathematica. I'm doing a parametric plot. Okay. And this is a function. So I've got my brackets here. And then on the inside, I've got my x and my y. Okay. And then I've got comma, and then I've got my domain for my parameter. So in fact, to be a little more specific, I've got x of t, y of t, okay, and then comma, and I've got my domain for the parameter t. I've got to tell Mathematica what the parameter is. The parameter is t, and tell it when to start and when to stop. So start at t equals negative 10, stop at t equals 10. Okay, and all of that is the argument of this parametric plot function. Okay, all right, and this is what the output looks like. Okay, if I wanted a smaller version, then I would need to change my domain and the domain of t. Okay, now over here, I don't know if you can tell, I've got arrows. So what I did was I created a function. I wanted to include this because this will be helpful for when you're doing your homework and creating your videos, creating your Mathematica input and output. So notice here's my input and here's my output. Okay, and I created a function. So at this row here, I am creating a function. And I'm defining it to be the square root of t and then 2 minus t. Okay, so this is my r of t. And then I'm defining dt to be an increment. And this is telling Mathematica how, basically, the increment of change in t that I want to take account. Because the next thing I do is I tell Mathematica to create a table, and the table is going to be a bunch of arrows. So remember, we had that's a built-in is an arrow, and for arrow, you put in the tail, comma, the tip, right? So I want to create my arrow, and I start at some point, f of t, and then when do I end? I want to end at f of t plus 0.2. So that's like telling Mathematica how frequently to sample your plot there, okay? And then lastly, I'm telling Mathematica to graph the table, the values of the table that I just created, right? And so remember that so see how this table here is lowercase? So I've got table equals, right? So I am creating a variable that's called table. And now for my next step, I'm telling Mathematica to perform this function on my variable table that I created back here. Does that make sense? So remember, if the function is uppercase, that means it is a built-in function. So table is built in, arrow is built in, square root is built in. Does that make sense? Graphics is built in. And then we can define variables like here. See, table, that's something that we defined. And we can define functions, but if you define something, then you have to have lowercase. We also defined dt. We could have called that something other than dt. But the reason why you would want to call it dt is because someone else who's looking and reading what you're doing will automatically get an idea that, oh, dt stands for the incremental, right? So that's the reason to do that. Now, once we have defined f and made our function f, then after that, so notice this is my input number 12, right? This is input, I don't know, number 8. And then I guess I deleted some stuff. Output was number 11. Input 12, I just put in that I wanted f of 1. Remember, f is a function, so I had to use brackets. And then I hit enter and f prime of 1. And the output, so this is going to be f of 1. And this is going to be f prime of 1. Okay, and this should, and I believe it does, equal exactly what we found doing it the long way. Does that make sense? Okay. All right, so you want to make sure that you have this handy because really what you can do is just cut and paste these formulas here and then modify it, right? So what do we mean when we say play around with it? Change 0.2. What happens if we set dt equal to 0.1? That means we should have twice as many arrows, right? We should have twice as many arrows. Does that make sense? What happens if we stop from 0 instead of 0 to 4? What if we take into account negative values, right? What happens if instead of 2 minus t, we switch that to 2 plus t? That's the benefit of using technology because it's so fast to investigate all these ideas that you have, right? Okay, now, yeah, so this is just rewriting the formula. We found that formula from before. That's the same thing as 1/2 t to the negative 1/2, comma, negative 1. And isn't that what we found for our formula for r prime? Yeah. 1/2 t to the negative 1/2, comma, negative 1. Okay. And notice here, if we wanted to compute this, if we wanted to compute that r prime, all we could have done was for an input in 14, input, right? We could have put f prime of t and then press shift enter, and then the output would have been, right, 1/2 1 over square root of 2t, 1 over 2 square root of t, negative 1. Okay, so yay, Mathematica. It's a really good way to check your work. The curve is a plane curve. Now, what does that mean? Plane means you're in 2D. So remember, plane is going to be 2D. Space is the term that you use for 3D. Okay, so a space curve would be like the helix we were talking about. A plane curve is, maybe a circle or something like that. So I'm going to clarify that. Plane versus space. Okay. And then this just talks about how to eliminate the variable to actually do your sketch. And here's the sketch here. Here's another thing that I would like to point out. What we can do is you can change the color in Mathematica. So I think there's some kind of option, right? So if you Google how to plot in blue in Mathematica, I think there is an option, like maybe it is something like blue and then arrow something something. right? So we could get it so that this graph here is, right, so that our graph is blue. We can also get it so we can also add a command or an option that will print little labels. Okay, so that's really important. And of course, as you saw on your quiz, you know how to make an arrow because you just, right, you have arrow, and then your starting point would be 0, 0, and your stopping point would be 1, 1, right? And then you know how to make another arrow which starts at 1, 1 and stops at, well, if your derivative was that r prime here? Okay, so let's think about that. So if we're starting at 1, 1, and we want to go 1/2 in the x direction and -1, that means we're going to go down 1. So then we should end up at 1.5, comma 0. Does that make sense? So 1.5, comma 0 should be the location here. 1.5, comma 0. So do you get what I'm saying here? So if we wanted to draw this pink arrow, we would need to tell it to start at 1, 1. And where's it going to stop? Well, we need to add 1, 1 plus add to it the r prime of 1, which is 1/2, comma -1. 1/2, comma -1. And so we end up with 1.5, comma 0. So, right, so we're moving 1.5 units in the x direction and then down 1 unit in the y direction. So 1.5, comma 0. And I think it's something like that, or it might be brackets in there. I'm not sure. You got to double check that. But so, okay, so good, good, good. Now, find parametric. Let's do this example here. Find parametric equations for the tangent line. Anytime you see tangent line, you should think derivative, right? Tangent, what gives us tangents? Derivative functions. Okay, so find parametric equations for the tangent line to the helix with parametric equations x equals 2 cosine t, y equals sine t, and z equals t at the point 0, 1, 1/2. Okay, so here's a way to think about this. First of all, we're given the hint that the graph is a helix, but how would we know that? Well, look at x, y, and z. There's a relationship here because if I have x, right, x is 2 cosine t, right? 2y is 2 sine t. Yes, so that means that x squared plus 2y squared is equal to, so that would be 4 cosine squared t plus 4 sine squared t. Pull out the 4, and we get cosine squared t plus sine squared t, which we know is equal to 1. All right, so that means that all of the points x, comma y satisfy this equation here. What is the graph of x squared plus 4y squared equals 4? That is an ellipse. Does that make sense? That's an ellipse. So it's going to come out 2, back here at -2, 1, and right? So it's an ellipse. So now we know that the x and y are following this pattern. And the last thing that's changing is z. So we're having height. So you're starting off with, so if we consider this point here, which would be 2 units up, and then you're coming here, come, right? Do you see how my drawing skills are kind of pathetic here? But do you get what's happening is that as you're going around the curve to make the ellipse, your height is increasing. Does that make sense? Yeah, that's better. That's better. Yeah, that's good. Okay, and then when t is negative, you're going down. So that's called a helix. And with the situation is we're concerned about, we want the equation for the tangent line at the point x is 0, y is 0, t is pi over 2. Or sorry, z is pi over 2. So we've got to figure out at what time are we at this location of 0, 1, pi over 2. So that looks like about here, right? So for what value of t are we at this location? Does that make sense? Okay. So our equations are 2 cosine t, sine t, t. So we got 2 cosine t, sine t, t. Okay. Now we know that our prime of t is going to be, what's the derivative of cosine? Negative sine. Negative 2 sine t. The derivative of sine is just going to be cosine t. And the derivative of t is going to be 1. Okay. Now, remember, in order to determine the equation for a tangent line, we need a point on the line and we need the direction of the line. Does that make sense? So it looks like we're looking at a direction like that, right? That's the line that we need. We need a point on the line. We've got it here. And we need the direction. We're going to get that direction by finding by the derivative, r prime. That's why we need to figure out t. So for what value is of t is r of t equal to 0, 1, pi over 2. So that's our question. And then our answer is, well, not so shabby, because look, do you see here? You got here. So we'll need 2 cosine t to equal 0, sine t should equal 1, and t should equal pi over 2. So this is easy, haha. It's easy because that means t is equal to pi over 2. So back here, when does this happen? This is occurring at t equals pi over 2. So this direction, we need to know r prime at pi over 2. And this will be the direction of our line. Okay, and then we've got our point. We've got our point right here. Okay, so the direction of our line is going to be r prime of pi over 2, which is going to be negative 2 sine pi over 2, comma cosine pi over 2, comma 1. Okay, what is sine of pi over 2? That is the y value, so that should be 1. So that should be negative 2. What is cosine? That'll be 0, 1. All right, so we've got a direction of the line and a point on the line. It's going to be, what is the point? 0, 1 pi over 2. 0, 1 pi over 2. So our equation for the line is going to be 0, 1 pi over 2 plus t times negative 2, 0, 1. Okay, and the last thing we need to do is convert from a vector equation to parametric equation. So what I just gave here is a vector equation. the last thing let's do is to convert this to a parametric equation. Okay. So let's see here. So here's how I like to do this. Plus t times -2, 0, 1. So the first thing I'm going to do is I'm going to turn it into, I don't need to do symmetric. I just need to do vector. So all I can do is I can just say x is equal to this plus this here, right? So let me show you how we're doing that. So I can rewrite this as 0, 1, pi over 2, plus, now this t is a scalar, so I can just multiply it in component-wise. So I've got -2t, 0, t, right? And how do we add vectors? We add them component-wise. So 0 plus -2t is going to be -2t. 1 plus 0 is going to be 1. And then pi over 2 plus t is going to be pi over 2 plus t. And now, for my parametric equations, I'll just have x equals -2t, y equals 1, z equals pi over 2 plus t. And these are the equations, parametric equations, for this line right here. Okay. Okay, so it looks like we've got some, answers here. Here we go. And the sketch wasn't that bad, just by using the fact that in the xy coordinate we'll have an ellipse and z is increasing. Now, between me and you, does it not look like Stuart uses Mathematica to create the graphs? I'm just saying. Because doesn't Mathematica put a little box in there? All right. We could actually look and check them. I think that it does. Okay. And now this is something to mention, that for real value functions, similar to real value functions, we can take second derivatives, right? So r double prime of t, you're just going to take the derivative twice in each component. Okay.